In 1938, something rolled out of LaGrange, Illinois that would kill an entire industry. Not gradually, not quietly, but in a transformation so complete that within 20 years, the technology that had ruled for a century would be almost extinct. The EMD-FT locomotive, powered by a pair of engines called the 567, proved that diesel could do what steam couldn't: show up, work, and keep working. But here's what made it truly revolutionary. Engineers said two-stroke diesels were too crude, too simple, too unrefined for serious railroad work. They were wrong. This is the story of the engine that silenced steam. Steam's golden age and hidden problems. Steam locomotives were magnificent machines. By the 1930s, designs like the Union Pacific Big Boy could haul 3,600 tons over mountain grades. The New York Central Hudson could hit 120 miles per hour with passenger trains. These weren't just machines, they were the backbone of American industry, the sound of progress, the technology that built a nation. But that sound came with a price nobody wanted to pay anymore. The maintenance nightmare. Every steam locomotive needed daily maintenance just to operate. Before a locomotive could leave the roundhouse, workers spent hours checking bearings, oiling valve gear, cleaning ash from fireboxes, and filling water tanks. That was just to start the day. After a run, the locomotive needed its fire cleaned, boiler washed, and countless mechanical parts inspected. A typical steam engine required 8 to 10 hours of maintenance for every 24 hours of operation. Do the math. That's a machine spending a third of its life in the shop before anything even breaks. When something did break, and things broke constantly, repairs meant weeks of downtime. A failed main rod bearing meant pulling the entire side rod assembly. A leaking boiler tube meant draining thousands of gallons, letting the boiler cool for days, and having specialized boilermakers crawl inside to replace tubes one by one. Each repair required craftsmen with years of training, expensive specialized tools, and facilities that only existed in major rail yards. Small railroads couldn't handle major repairs. They had to deadhead locomotives hundreds of miles to shops equipped for the work. The economic death sentence. The numbers told a brutal story. A freight steam locomotive might be available for service 60% of the time if maintenance went smoothly. The other 40% it sat idle, earning nothing while consuming resources. Railroads needed to own 30 to 40% more locomotives than they actually operated just to maintain service schedules. Each locomotive tied up in maintenance represented dead capital, lost revenue, and fixed costs that never stopped. Insurance companies knew steam's reputation. Boiler explosions killed. High-pressure steam could turn a small leak into catastrophe in seconds. The operational costs added up fast. Steam locomotives needed water stops every 100 miles. In the western United States, that meant building and maintaining water tanks in the middle of nowhere, staffing water stations around the clock, and dealing with seasonal shortages. Coal or oil had to be loaded, often by hand, at fueling stations that required their own infrastructure and workers. Each locomotive needed a two-man crew. An engineer ran the throttle and brakes, a fireman shoveled coal or adjusted oil burners, managed water levels, and watched steam pressure. Even when a locomotive sat in a yard between runs, someone had to maintain the fire or face hours of startup time when needed. By 1930, railroads faced a crisis. The Great Depression crushed freight traffic. Highway trucks, freed from rails, cherry-picked profitable short-haul business. Passenger cars and intercity buses competed for travelers. Steam's high fixed costs, even with reduced traffic, pushed railroads toward bankruptcy. Something had to change, but electrification required millions in overhead wire infrastructure. Diesel seemed like the answer, except early diesel engines kept failing. General Motors takes on the challenge. General Motors saw an opportunity. They bought Winton Engine Company and Electromotive Corporation in 1930, combining automotive manufacturing expertise with railroad knowledge. Winton's 201A diesel engine powered the Burlington Zephyr Streamliner in 1934, setting speed records and capturing public imagination. But behind the headlines, the 201A suffered constant failures. Pistons cracked after 50,000 miles, cylinder heads warped, connecting rods broke. Railroads trying diesel switchers experienced frustrating breakdowns that made steam look reliable by comparison. The technology worked on paper. In practice, diesel engines designed for ships and stationary power plants couldn't handle railroad duty cycles. Charles Kettering, GM's research director, put his son Eugene in charge of designing a railroad engine from scratch. The team at LaGrange started in 1936 with one rule: keep the two-stroke cycle, throw away everything else. In No parts from the 201A, no compromises. Build an engine specifically for what railroads needed, not an adaptation of something else. Engineers focused on three things: high torque at low speeds, reliability measured in years not months, and maintenance that didn't require specialists. The 567 design revolution. The 567 got its name from displacement, 567 cubic inches per cylinder. For comparison, a modern car engine cylinder holds maybe 30 cubic inches. Each cylinder in the 567 displaced more volume than an entire four-cylinder automobile engine. The smallest version of V6 configuration totaled 3,402 cubic inches. The largest, a V16, reached 9,072 cubic inches of displacement. That's bigger than some building-sized stationary engines. But displacement alone meant nothing without the engineering to make it work. The two-stroke design meant every revolution of the crankshaft produced a power stroke, doubling the firing frequency compared to four-stroke engines. Critics said two-stroke engines wasted fuel, produced too much smoke, and wore out quickly. EMD's engineers solved those problems with uniflow scavenging. Air entered through ports in the cylinder liner near the bottom. 4 poppet valves in the cylinder head let exhaust gases out. Fresh air never mixed with exhaust. The scavenging process happened in milliseconds as the piston moved down, and it worked perfectly every time. A Roots blower forced air into the cylinders under pressure. Unlike turbochargers that depended on exhaust energy, the mechanically driven Roots blower provided consistent airflow at any speed. At idle, it scavenged exhaust gases and filled cylinders with fresh air. Under load, it packed maximum air into each cylinder during the brief moment the ports were open. This solved the fundamental problem with two-stroke diesels, getting enough air for clean combustion. The Roots blower's characteristic whine became the signature sound of every 567 powered locomotive. Each cylinder got its own unit injector, a self-contained system combining high-pressure fuel pump and injection nozzle in one unit. The engine's camshaft actuated the injectors, providing precise timing without vulnerable external fuel lines. When an injector needed service, mechanics swapped it out in minutes. No bleeding air from fuel lines, no adjusting multiple components. Just unbolt the old one, bolt in the new one, done. The unit injector design eliminated most fuel system failures. The crankcase used welded steel construction formed into a rigid V shape. Unlike cast iron crankcases that could crack from thermal stress, welded steel flexed slightly under load and returned to shape. The crankshaft sat at the bottom of the V, supported by massive bearings at each throw. This configuration kept the engine compact while maintaining the rigidity needed to handle 16 cylinders firing in rapid succession. The entire crankcase acted as a structural member, eliminating the need for external support frames. Pistons evolved through several designs before engineers settled on a floating construction. Early versions used aluminum with steel crowns. Thermal stress cracked the junction between metals. Cast iron worked better for the extreme temperatures at the top of each cylinder, but pure cast iron pistons were too heavy. The final design used cast iron with carefully designed passages that let lubricating oil flow through the piston body, carrying heat away. This cooling method extended piston life from 100,000 miles to over 500,000 miles between replacements. Cylinder liners could be removed without disturbing the engine block. A wet liner design meant coolant surrounded each liner. Mechanics could pull a liner out as a complete unit with an overhead crane. The liner included precisely shaped ports for air intake, positioned to prevent the piston rings from catching on port edges. Silicone rubber seals at top and bottom prevented coolant leaks and could last 750,000 miles in service. When a cylinder needed attention, removing the liner exposed everything for inspection or replacement. What really makes the 567 sound? Here's where people get confused about what really makes the 567 sound the way it does. Everyone credits turbochargers, but most 567s used Roots blowers, not turbos. That characteristic two-stroke rhythm comes from the firing sequence. Every crankshaft rotation produces a power stroke, creating that rapid chuff inside of steam's slower beat. The Roots blower adds a mechanical whine that rises and falls with engine speed. Exhaust valve timing creates the distinctive rhythm. 4 valves per cylinder open just after peak pressure and closed as the piston uncovered intake ports. This precise timing had to stay within a few degrees, or the scavenging process would fail and power would drop dramatically. But here's the part that confuses everyone. Many locomotives identified as having 567 engines today actually run 645 power assemblies inside 567 crankcases. The 645 series, introduced in 1965, used larger cylinder bores and longer strokes. EMD designed 645 power assemblies to fit 567C and 567D engine blocks, letting railroads upgrade without replacing complete locomotives. These hybrid engines perform like 645s but keep the external appearance of 567s. The upgrade path meant perfectly functional locomotives get more power and modern components without the expense of new units. Why engineers doubted diesel. Steam locomotives looked more powerful. They had huge driving wheels, massive boilers, external valve gear that moved dramatically with every stroke. Diesel-electric locomotives seemed smaller, simpler, less impressive. Railroad executives worried that customers would think diesel meant cheap or inadequate service. Engineers who'd spent careers mastering steam thermodynamics looked at diesel-electric transmission and saw unnecessary complexity. Why not use the diesel engine to drive the wheels directly through gears like a truck? Because trucks don't weigh 400,000 pounds and haul 10,000-ton trains up mountain grades. The diesel-electric system. The diesel-electric system worked like this. The diesel engine ran at constant speed, typically 800 RPM for the 567, regardless of train speed. The engine drove a large generator that produced electricity. That electricity fed traction motors mounted on the locomotive's axles. The traction motors turned the wheels. By varying the electrical current to the motors, engineers could control train speed from 0 to maximum without changing engine speed. This electric transmission provided infinite speed control, let the diesel run at its most efficient RPM, and eliminated the complex mechanical gearing that would have been needed for direct drive. Multiple unit control changed everything. One engineer in the lead locomotive could control engines and following units through electrical cables. Need more power? Add another locomotive. 567 enabled this because identical engines in different units synchronized perfectly. Steam locomotives could be double-headed, but that required a crew in each locomotive and careful coordination to avoid breaking couplers or damaging equipment. Diesel multiple unit operation meant one crew could handle 10,000 horsepower or more by linking several locomotives. Dynamic braking turned traction motors into generators when descending grades. Instead of burning brake shoes trying to control heavy trains on mountains, engineers could make the diesel engines absorb energy as electrical resistance, converting momentum into heat dissipated through massive cooling grids. This saved brake maintenance and made operations safer on steep grades. Steam locomotives had no equivalent capability. Mountain railroads had to add helper engines, maintain brake shoes constantly, and hope runaway trains didn't happen. The power assembly revolution. The real genius wasn't the engine itself, it was the power assembly concept. Each cylinder formed a complete self-contained module. The assembly included cylinder liner, piston, connecting rod, piston carrier, and cylinder head, all bolted together as one unit. When a cylinder needed service, mechanics didn't tear down the engine. They unbolted the power assembly and lifted it out with an overhead crane in a few hours. A rebuilt assembly went in the same day. The locomotive returned to service while the removed assembly went to the shop for rebuilding at leisure. This changed everything about railroad maintenance. Steam locomotive repairs meant specialized craftsmen, weeks in the shop, and complete disassembly of major components. A power assembly swap needed general mechanics, a crane, and standard tools. A railroad could pull a power assembly in the morning, install a rebuilt unit by afternoon, and have the locomotive hauling freight that evening. The modular design slashed downtime from weeks to hours. That meant availability jumped from 60% to 90% or better. Suddenly, a railroad could operate with the number of locomotives they actually needed instead of maintaining a huge reserve fleet. Parts commonality multiplied these advantages. Whether a railroad owned V6, V8, V12, or V16 engines, the power assemblies were identical. The same cylinder liner fit every engine. The same piston, the same injector, the same valves. One parts inventory served the entire fleet. Mechanics trained on one engine could service them all. The economies of scale were unprecedented. When EMD introduced improvements like better pistons or upgraded injectors, those upgrades could be installed during routine power assembly changes. The 567 could evolve over its service life without replacing the complete locomotive. The FT proves diesel works. The EMD FT demonstrator hit the road in 1939. 4 567 powered units totaling 5,400 horsepower. Over the next year, it toured 20 railroads, hauling their heaviest trains over their toughest routes. The FT pulled loads steam couldn't handle on grades where steam needed helper engines. Operating costs came in at 5 cents per mile compared to steam's 10 cents. Fuel efficiency doubled. Maintenance took hours instead of days. Most importantly, the FT didn't break down. It just worked, mile after mile, month after month. World War II halted civilian diesel production. The Navy needed diesel engines for submarines. Locomotive production shifted to steam and existing diesel engines, but railroads that had tested the FT couldn't forget what they'd seen. When the war ended in 1945, orders flooded in. EMD's LaGrange plant, expanded during the war, couldn't build locomotives fast enough. The dieselization wave began, the rapid transformation from steam. Western railroads adopted diesel fastest. Water scarcity in states like Nevada and Arizona made steam operation expensive. Hauling water tank cars to remote locations cost money. Diesel locomotives could run thousands of miles on a tank of fuel, needing only periodic refueling at major terminals. The Santa Fe, Southern Pacific, and Union Pacific ordered diesels in huge numbers. Their steam fleet shrank rapidly through the late 1940s. Eastern railroads followed. The Pennsylvania Railroad, the largest in the country, began replacing steam in 1946. By 1948, steam's share of new locomotive deliveries dropped by 2%. By the mid-1950s, 90% of American steam locomotives had been scrapped or retired. The GP series changes everything. The GP7 road switcher, introduced in 1949, became diesel's breakthrough product. Previous diesels fell into categories: streamlined passenger units, heavy freight units, or yard switchers. The GP7 did it all. At 1,500 horsepower from a 16 567B engine, it could handle yard switching in the morning, then head out on a freight run in the afternoon. The versatility meant railroads needed fewer specialized locomotives. Production ran from 1949 to 1954 with 2,610 units built. The GP7 established the road switcher as the standard American locomotive type. The GP9 followed in 1954 with upgraded electrical systems and 1,750 horsepower from a 567C engine. Another 4,157 units rolled out through 1963. GP9 served on every major railroad and hundreds of short lines. Many are still working today, 70 years later, on short-line railroads and industrial service. The design proved so successful that EMD kept refining it through GP18, GP20, GP30, and GP35 models, all powered by 567 variants pushing toward 2,500 horsepower. Switchers and passenger power. Switcher locomotives use smaller 567 engines for yard work. The SW1, SW7, SW9, and SW1200 models range from 600 to 1,200 horsepower with V6 and V12 engines. These locomotives spent their lives starting and stopping constantly, assembling trains and classification yards. The 567's two-stroke design handled this duty cycle better than four-stroke competitors, which suffered carbon buildup and poor combustion at low loads. Thousands of switchers operated around the clock in major yards, replacing steam switchers that needed constant attention. Passenger service demanded different priorities. The E-Unit series, powered by twin 12-567 engines and streamlined car bodies, could maintain 100-mile-per-hour schedules while providing steam-like reliability. Unlike steam locomotives that needed water stops and coal changes, E7, E8, and E9 models could run coast to coast with only fuel stops and routine inspections. The twin-engine configuration provided redundancy. If one 567 failed, the unit continued on the remaining engine at reduced speed. This reliability proved crucial for passenger trains operating on tight schedules with no backup equipment. The human cost of progress. The transition wasn't smooth for everyone. Coal-producing regions resisted diesel because steam locomotives consumed the coal that local mines produced. Norfolk and Western Railway, serving Appalachian coal fields, held on to steam until 1960, developing advanced designs like the J-Class streamlined passenger locomotive and the Y6B articulated freight engine. But even N&W eventually accepted that diesel's advantages outweighed regional loyalty. The last significant steam operations ended by 1960. Steam locomotive firemen found themselves obsolete. Union agreements required railroads to keep firemen in diesel cabs even though diesels didn't need them, leading to decades of labor disputes. Roundhouse workers who'd spent careers maintaining steam engines had to learn completely different skills or find new work. And Entire support industries disappeared. Builders of steam locomotive parts, coal handling equipment, water tank systems, and specialized tools went out of business. Communities built around division points where steam locomotives changed crews and took on supplies saw jobs vanish. Beyond the railroad, the 567 found life beyond railroads. Marine conversions put 567 engines in tugboats, fishing vessels, and military landing craft. The Navy's LST ships used 567s modified for marine service with altered sumps that handled the motion of ships. Stationary power installations put 567s in hospitals, industrial facilities, and remote locations needing reliable backup generators. The same characteristics that made them ideal for railroad service, constant speed operation and bulletproof reliability, translated perfectly to these applications. Industrial operations discovered 567 engines were perfect for driving equipment needing constant reliable power. Sawmills, mining operations, manufacturing plants installed 567 power generators and compressors that could run continuously with minimal maintenance. Oil fields and remote locations used 567s to power drilling equipment and pumps. The engines that had revolutionized railroading kept American industry running in places where electrical grid connections didn't exist or couldn't be trusted. The legacy lives on. Today, 567 engines continue operating in applications where newer technology can't match their combination of simplicity and durability. Tourist railroads rely on 567-powered locomotives to haul passengers on scenic excursions, often the exact same units that hauled freight in the 1950s. Shortline railroads operating with tight budgets prefer 567-powered switchers because parts remain available and mechanics understand the simple, robust design. Industrial switching operations use vintage 567 locomotives because they're paid off, fully depreciated, and still work. Preserved 567-powered locomotives run at railroad museums across the country. Restoration groups have become expert at rebuilding these engines, sometimes installing 645 power assemblies for emissions compliance or parts availability. The sound of a 567 at idle, that distinctive two-stroke rhythm with roots blower whine, triggers nostalgia for the era when these engines represented cutting-edge technology. Heritage railway operators have learned that maintaining 567s is often easier than maintaining steam locomotives, with fewer specialized skills needed and better parts availability. The 567 production run ended in 1966, succeeded by the 645 series with larger displacement and higher power output. The 645 eventually gave way to the 710, and modern locomotives use microprocessor controls and emissions equipment the 567's designers never imagined. But the fundamental architecture established by the 567 persists. EMD's current engines still use two-stroke uniflow scavenging, unit injectors, and modular construction. The innovations developed for the 567 enabled everything that followed. Looking back, the 567's impact went beyond just replacing steam. It redefined what railroad power meant. Before diesel, power meant peak horsepower and dramatic displays of mechanical motion. The 567 proved that power meant availability, reliability, and economics. A locomotive that shows up every day and works is worth more than one that produces more peak horsepower but spends weeks in the shop. This lesson applied far beyond railroads. The shift from impressive mechanical complexity to simple, reliable systems happened across industries, often following the pattern the 567 established. The engines that silence steam have themselves fallen mostly silent. Modern diesels with computer controls and emission systems dominate railroad operations. But in switching yards, on short lines, and at tourist railways across America, you can still hear that two-stroke rhythm. The roots blower whine, the sound of an era when one engine changed everything. They showed up, they worked, they kept working, and some of them still do.